Hi, I'm Grimur and this is my assignment, a puzzle for class CSC480. And 2 minutes, so I ran it just, so let's look at that. And it's a driver class you run, and then you enter your difficulty for a state problem, and then the algorithm runs it. And then what we got for each algorithm, we got an action, then we got a cost, and then we got a total cost. We can see breadth first search, all these costs, and there's a total cost 17. This is depth first search, which is pretty huge. We can see right before I hit medium are all the other algorithms. As for medium, here's breadth first search, depth first search again. Right before hard, here are all the other ones. And as for hard, breadth first search, depth first search is a little bit lower now. And these are all the codes that we're running. Moving on to my code, let's look at my a puzzle node first. As we can see, we have our parent state, our bookkeeping for all our debts, the costs, the nodes visited, all that, and importantly our children. And then we have our puzzle service, which is used for successor function. And we got our node cost, which is used for some algorithms, and our f cost used for other algorithms. And then there's a basic cost as well, which we use no cost as well. What's most important here is our successor function, and that's when we do set children. Is right here. We use our puzzle service. We go to puzzle service right here. We can see we do our state goes in here, and the node goes in here. Then we have combinations of left, right, up, and down, which will be sent to a puzzle factory children, and that has our state, the node that comes in, and our action. It will find where the 0 is found in the current state, and then the value will be set that's going down, and then the other value will be set as 0. And it's pretty much like the same for every image. If there's one that's out of bounds, there will be a no, and when it gets sent back to our puzzle service, it will be ignored if it's just a no. Now, looking at our algorithms, if we go to A*1, A*1, A*2, A*3 are pretty similar. If we look at our loop, we have a priority queue extra, which is our f cost, and our f cost is actually for A*1, it's actually our get node cost plus our misplaced cost. The get node costs are calculated with the current get node cost and the child cost. And the f cost is then the node cost plus our misplaced tile in A*1. So whatever this value is, the lowest value that's added to our minimum priority queue here will be set out first from here. And also I can just say it right away for duplicates, it's always in our list, it gets converted our state, and it then gets added to the list. Then we check if the integer is here. As for A*, it's going to see if there's a better node cost available. There's a lower path as it traverses the tree. If there is, it will take that node and set it to the lower one and then set it to parent. As for the other one, it just checks if there's a duplicate. If there isn't, it will check its cost. If it's higher, then we're going to set it to the lower one, and then we'll put it to our list of cost. And A*2, exactly the same, except there's a Manhattan distance instead of our misplaced tile. I'll explain heuristic service later. As for A*3, still working on that. I'll explain more in the heuristic service, but I was trying to do the pattern. As for best first search is actually a priority queue, only my priority queue. And if we look up here, that's based on our node cost. It could be a little bit different for each algorithm. So misplaced only looks at a misplaced tile. For every node cost, misplaced tiles. So whatever that is, we'll add it to the queue, take its minimum out, and then go run with it again. Every algorithm sets its children as well and checks for duplicates. As for breadth first search, we have in our main loop we have first in, first out list, array list. We add our source, then we get it out. Children are set. Go through these children. Set it step, set children. Add it to the list, and then we remove first. We just need it for traversal in breadth first search. As for depth first search, exactly the same, except we have a first in last out, which is called an array deck, which is actually a double linked list, which makes it possible to do a push and a pop. So it's the same here. We have pop, and then we do a push when we add, as we can see here. As for iterate depth, it's a combination between breadth first search and depth first search. So in our main loop here, we iterate at 3 depth. For each depth, we do a breadth first search first, you could say. And after that's done, after that 3 is ready to go, it's sent into a depth first search with that depth. If there's ever a goal find, right here, it'll be set, and then the main loop will find it, and then the algorithm is done, and it will be sent with the output. Final one, uniform search. That one has actually a priority queue, which is based on the node cost plus the child cost. So that will go through all the way. Same here, it has also a duplicate list. If it's ever found, it will check if there's a better path, set a parent, else. If it's not a duplicate, we're gonna set it to the cost it needs, and then the minimum will be sent to the priority queue. If I didn't say before, I'll just say it again. These are in every algorithm. It checks if it's a goal. If it goes, it will always stop. That's the main one we need to output our solution. But then we return and we can put it for output. Service, and if we start with our misplaced tiles, which is pretty simple, we just go to our start compared to a goal. If one of them are not equal, we count to 1, keep going, and then we return 1. These two were actually part of my A-star 3 I was starting on, where I was going to do the first subproblem, count those, and then I was going to keep those and then keep going from like goal all the way up to like a start node with breadth first search, but I haven't done that yet. And as you can see, here's the main loop for that. A basic Manhattan distance, it actually has a helper, because every number needs to be compiled, like from where it is to its goal. So we have a Manhattan node, which is basically just a number and its coordinates, and then the Manhattan distance helper will just take a straight line distance from the goal, where the goal is, minus the number's position, and then those x's and y will be returned. And that is it.